As dental professionals, we must have an understanding of the X-ray machine, its parts, functions, and how the machine creates ionizing radiation or X-rays. Chapter 3 talks about the dental X-ray machine, its components, and functions. Before we move on to Chapter 3, let's do a review of what we've talked about in Chapter 1. In Chapter 1, we've defined radiography, that it is the art and science of making radiographs by using image receptors, which can be film, phosphor plates, or digital sensors. We've talked about our goal, that as radiographers, we need to produce the highest quality radiographs while keeping the dose as low as possible. We've talked about the purpose of radiographs, that radiographs are used as diagnostic tools and majority of dental procedures cannot be done without radiographs. We've also talked about the discovery that on November 8, 1895, a German physicist named William Conrad Röntgen discovered X-rays. And then months after his discovery, we have different scientists who contributed to the development of X-rays. We have Dr. Wotkoff. He was the first to produce dental radiographs in Europe. And then Dr. Seekels, who was the first in the United States. Dr. Rollins suggested that radiographers need protection while taking radiographs to prevent them from having overexposure, so he was named the father of radiation protection. We also have Dr. Coolidge. Dr. Coolidge invented the first X-ray machine that is shock-proof. Dr. Raper, he was the first to publish a book on dental radiography, and he was the first who suggested the bite wing technique in 1925. We also talked about the dental X-ray machines and compared what we have before from what we have right now. Before, the wires are exposed, the tube head was exposed, but now the tube is in the tube head, it is shock-proof, and it has all the features to prevent the radiographer from getting electrocuted. We also talked about digital imaging. That digital imaging was introduced by Francis Boyen in 1987, and it showed a great reduction in the radiation needed to produce radiographs. We also talked about the dental X-ray films, that older dental X-ray films, well, it started with a glass photographic plate wrapped in paper to prevent moisture from contacting the plate, and then later on the hand-wrapped dental X-ray machine with only one side with emulsion, and then the newer dental X-ray machines have emulsion, dental X-ray films have emulsions on both sides of the X-ray film. We also talked about the image receptors, that digital image receptor require less radiation, so the patient is not getting as much radiation as compared to what we're using before to create a radiograph. Then panoramic X-ray machines, we discussed that it was introduced in 1948, but it did not get popular until 1960s. We also talked about the dental X-ray techniques. We have two. We have the bisecting technique and the paralleling technique. Paralleling technique is the technique of choice because it produces a better quality radiographs as compared to the bisecting technique, and we are going to learn and to know why we would rather use the paralleling technique than the bisecting technique. And then lastly, we've talked about the uses of dental radiographs. So now we are going to proceed to Chapter 3. Chapter 3 looks at the different parts of the dental X-ray machine. Dental X-ray machines may vary slightly in look and design, but they will have the same basic parts. The three main parts of a dental X-ray machine are the control panel. The control panel contains the regulating devices, so this is this one. And these regulating devices regulate the exposure time and controls how much radiation is generated. This is also where electricity enters the X-ray machine. We have the tube head. The tube head is where the X-rays are formed, and it contains the X-ray tube. And then the extension arm, it is also known as the bracket, holds the tube head and helps with positioning. It also suspends and enables movement of the tube head. Let's talk about the control panel. Control panel is where the unit is plugged into an electric current. So, electricity is the source of energy for X-ray production. You need to remember that electricity is the source of energy for X-ray production. So going back to the control panel can be mounted on a shelf, on a wall, or it can be integrated into the tube head. One control panel may serve more than one X-ray tube head. There are 5 major controls on the panel. We have the line switch, we have the milliamperage or MA selector, the kilovolt peak or KVP selector, the timer, and the exposure button. Older X-ray machine units allow the operator to change and select the needed milliamperage and kilovoltage, but the modern machines have preset controls like the X-ray machines that we have in lab. So again, electricity is the source of energy for X-ray production. Let's focus on the line switch. We are still talking about the control panel. The line switch is also known as the on and off button. So it controls the electricity going to the control panel. This is the line switch. There are different types of switches. It can be a toggle switch, it can be a push button, it can also be a keypad button. The locations are usually on the side or face or under the control panel. The control panel also has an indicator light that warns the operator and the patient that the machine is operational. And federal regulations now require that all machines have an audible tone when the unit is turned on and when an exposure is being made, to also alert and warn the operator that X-rays are produced. So this is part of the safety in radiology, the indicator light and the audible tone. Next is the milliampere selector or the milliamperage selector or the MA selector. This measures the amount of electrical current traveling through the wires of the circuit. Milliamperage determines the number of free electrons at the X-ray tube. Therefore, it determines the amount of X-rays that will be produced. So setting the milliamperage will determine how much X-rays will be produced. Milliamperage selector can be adjustable, where you would set it yourself, or it can be preset, like the ones that we have in lab, where it is connected directly to the on and off switch. So once you turn the X-ray machine on, it will automatically be at 7 milliamperage setting. So our machines will also have this one right here that says that we are using 7 milliamperage to produce an image. Again, milliamperage, amount number, and how much X-rays are produced. Next is the kilovolt peak or kVp selector. This measures the voltage that travels across the X-ray tube. This determines the speed of the electrons and determines the penetrating ability of X-rays. On newer X-ray machines, kilovolt peak selector comes in form of icons of a small, medium, or large patient because kilovolt peak is linked to the penetration of large or small patient. When the size of the patient is changed, the X-ray unit itself adjusts the milliamperage to maintain the film density. Kilovolt peak is also linked to the exposure time on the machine. Looking at the picture that we have on the slide, you can see the icons, and these icons determine the kVp that is needed to produce an image. Acceptable range for dental radiography is 60 to 100 kVp, and you need to remember that. Acceptable range, 60 to 100 kVp. If your kVp is below 40, it will not give as adequate amount of voltage needed to penetrate the object. If it is between 60 or 40 to 60, it can produce a lot of unneeded radiation. It would penetrate the object, but with secondary radiation. And we are going to learn that more when we discuss Chapter 2. So again, milliamperage, the amount, the number, how much X-rays produced, kilovolt peak, the speed, the penetrating ability of the X-rays produced. Now we have the timer. So we are still looking at the control panel, and on the control panel we have the timer. The timer regulates the duration of the interval that the current will pass through the X-ray tube. The timer sets our exposure time. In the machines that we have in lab, the timer is linked to kVp. So if you choose a large patient icon and switch it to the small patient icon, you will see that there will be a change in the exposure time. The exposure time for small icon is less as compared to the large icon. So looking at our X-ray machine, since electricity is the source of energy, the current comes in impulses instead of a steady stream of electricity or radiation. Those impulses are measured. We have 60 impulses per second, and you need to know that. 60 impulses per second. We also have electronic timers on our modern units that are very accurate, that they can measure 1/100th of second interval. But in our machine, we have 60 impulses per second. And since we have these newer films and we have digital receptors, which are faster and more sensitive, the exposure time has been greatly reduced. Again, sticking to our goal of producing the highest quality while keeping the exposure as low as possible. So, what would happen if you set the timer too long on a small patient? The image that will be produced will be too dark because there's too much radiation getting on the film. So remember, when we've talked about kVp, when the size of the patient is changed, the X-ray unit itself adjusts the milliamperage to maintain the film density. And if a small patient is exposed longer, then it will produce more X-rays, the penetrating ability will be high, so the image that will be produced will be darker. Next, we have the exposure button. This activates X-ray production in the X-ray machine. It must be located at least 6 feet away from the X-ray tube head or in a protected area. Without depressing the exposure button, no X-rays could be formed. So locations, they can be in several places. It can be away from the tube head. It can be on the control panel. It can be on a long cord. Or there are some machines with remote controlled exposure button. So again, the operator should be at least 6 feet from the source of radiation. Also, all machines have what we call a dead man switch. So when we say dead man switch, once you press the exposure button and then you release it, it will automatically end the exposure. So even if you're not done with your exposure, it will automatically stop, and that's called the dead man switch. Also, you should always listen for a beep or look for the light on the control panel to light up when you're exposing. Again, the audible beep and the indicator light are required by law, and those indicate that the machine is already turned on or X-rays are generated. Again, for the protection of the patient and the operator. Let's move on to the extension arm, which is one of the 3 parts of the X-ray machine. The extension arm provides support for the X-ray tube head. This is the extension arm. This is the extension arm right here. So it allows for moving and positioning the tube head. The tube head, which is this one and this one, is attached to the extension arm by means of a yoke. So the yoke will be in this part and this part. So the yoke. The yoke allows the tube head to move a full 360 degrees around. So it lets the tube head revolve 360 degrees horizontally, or it can be rotated vertically within the yoke. As you can also see here, you will see that the extension arm right here provides insulation to protect the patient and operator from electric shock. So the X-ray or the extension arm is hollow, and inside the extension arm are all the electrical wires going from the control panel through the X-ray tube head. The X-ray tube head is finely counterbalanced in its extension from the extension arm. So if it is left suspended for long periods, the counterbalance is upset. So that's why after we use our X-ray machines, we want to park the X-ray machine, the extension arm and the tube head against the wall with the PID pointing down to maintain the counterbalance. Because if we lost the counterbalance, then it can lead to drifting tube head, which will lead to upset students. The last basic part of an X-ray machine is the X-ray tube. Sometimes it is called the tube housing. This is tightly sealed. So this is the X-ray tube head. This is tightly sealed with heavy metal. It is lead lined. It usually has cast aluminum. It contains the X-ray tube, insulating oil. It also contains step up and step down transformer. So the main purpose or the purposes of the metal housing or the tube head is for the protection of the X-ray tube. So this protects the X-ray tube from damage. Electrical ground. So this grounds high voltage components to prevent shock. The tube head also prevents overheating because the tube inside the tube head is surrounded with oil or gas to absorb the heat created during X-ray production. One of the purposes is also for radiation safety because it is lined with lead that absorbs any X-rays produced except for the primary D beam. So meaning this helps prevent scatter radiation or secondary radiation. So newer X-ray machines are becoming smaller and more lightweight. So we are going to study the X-ray tube as we move along this chapter. As mentioned, electricity is the source of energy in X-ray production. So electricity is needed to produce dental X-rays. So it is necessary for us to have understanding of the basic electrical concept and terminology. Let's start with electricity. Electricity can be defined as electrons in motions. And to produce X-rays, there are two electrical circuits that are used. First is the filament circuit. Second is the high voltage circuit. Let's talk about the filament circuit. The filament circuit provides low voltage between 3 to 8 volts to produce and generate the source of electrons for the production of X-rays. And high voltage circuit provides high voltage between 50 to 100 kVp or kilovoltage that is necessary to accelerate the electrons and produce X-rays. Don't worry about the other words. We're going to talk about it again when we talk about the X-ray production. So, how do you think is it possible that electric currents can be changed in an X-ray machine even if there's only one source of electricity, which is the outlet on the wall? So, how is it possible that from 110 volts from the outlet, the electricity is converted to 3 to 8 to produce or generate the source of electrons, and then between 3 to 8 volts is changed between 50 to 100 kVp to finish the production of X-rays? The answer is because of the transformer. A transformer is an electromagnetic device for changing the alternating current. Remember that the current goes back and forth 60 impulses per second. So transformers are used to decrease or increase the current that enters the machine. We have three types of transformers. We have the step-down transformer, step-up transformer, and the auto transformer. The step-down transformer supplies or decreases the voltage from the outlet, so from the wall to the machine. So step down is the low voltage transformer. The step up is the high voltage transformer, which increases the voltage to propel the electrons once the exposure button is pressed, and we are going to talk about that again later. And then we have the auto transformer, or what we call the voltage compressor. This corrects minor fluctuations in the current that is flowing through the wires. When we're talking about electricity, we need to be familiar with specific terms, and the first is the amperage. Amperage is the unit of quantity of electric current. So the number of electrons. Increase in milliamperage results in an increase in the number of electrons that are available to travel within the tube head. This now results in a production of more X-rays. Dental X-ray machines use a small quantity of amperage that it is measured in milliampere. So a small amount of electricity is needed to operate an X-ray machine, and an ampere or 1 ampere is 1000 milliamperage. Most dental X-ray machines operate at 4 to 15 milliamperage. The amperage can be preset in a machine by the manufacturer, or it can be varied by the operator. So we've talked about milliamperage selector, right? So milliamperage, ampere, the quantity, the number, the amount. If you increase the ampere or you increase the milliamperage selector, it will result an increase in number of electrons that results in production of more X-rays. The next term is voltage or volt. This is sometimes called potential difference, and it is defined as the electrical pressure between two electrical charges. In dentistry, voltage or volt determines the speed of the electrons traveling within the X-ray tube. It determines the speed and the penetrating ability of the energy or X-ray produced. When the voltage is increased, the X-rays move faster, therefore a higher penetrating ability, and the harder the X-rays. Because dental X-ray machines use very high voltage, the voltage is expressed in kilovolts. A kilovolt equals 1000 volts. However, even with a high voltage, a polychromatic beam is still produced. So this means that the beam with varying intensities containing high energy X-rays and soft energy X-rays. We've also talked about the kilovolt peak or kVp. So the kilovolt peak is the highest voltage to which the current in the tube rises during an exposure. Machine controls are set to 60,000 volts and has the capacity to produce 60 kVp. And as mentioned, most dental X-ray machines operate with a range of 60,000 to 100,000 volts or 60 to 100 kVp. Let's talk about electric current. We have two types of current. It can either be a flow in one direction, which is direct current, or flow in pulses or flow that changes in direction or alternating current. Let's talk about alternating current first. Alternating current is the power supply in the United States in a typical household current, which can either be 110 volts, which is the normal plug, or it can be 220 volts. It is called alternating current because the current changes in direction of flow 60 times per second. It has two phases. We have positive, so this is an impulse. So from here to there is one impulse. So we have positive, and then we have negative. So it is called alternating because it changes from positive to negative back to positive. Dental X-ray machines using alternating current are programmed to only produce X-rays when the current is flowing in the appropriate positive-negative direction, resulting in bursts or impulses of X-ray output. So X-rays are only produced if the direction is on the positive side, and no X-rays are produced when the impulse is on the negative side. So even if the kilovoltage fluctuates from 0 to 70, the actual output is just 35 because X-rays are just produced whenever it is in positive direction. Next is the direct current. So current flows continuously in one direction. Dental X-ray machines using direct current produce more constant flow of X-rays and at a more consistent voltage. So X-rays are produced and it eliminates the alternating cycles. Historically, dental X-ray machines have utilized alternating current, but now we have dental X-ray machines with alternating current and we have dental X-ray machines using direct current. They both produce acceptable quality radiographs with films and digital receptors. Studies showed that dental X-ray machines using direct current may produce more consistent exposure at very short exposure times when we use digital sensors or digital radiography, which will slightly shorten the exposure time and reduce patient radiation exposure. Because digital receptors in the first place require a shorter radiation exposure than the films do. So dental X-ray machines using direct current typically operate at 50 to 65 kV, and alternating current dental X-ray machines typically operate 70 kVp or higher. So the change in kilovoltage setting may affect the radiographic image contrast. So if we use a dental X-ray machine that uses direct current, then the kVp that will be produced will be at the maximum of 65 kilovoltage. And as we've learned earlier, great or better quality radiographs can be produced if the kVp is between 60 to 100. So a slight reduction in kilovoltage to reduce the exposure of the patient may affect radiographic contrast. Let's talk about X-ray production, and let's start with the X-ray tube. Located inside the tube head is a glass bulb from which the air has been pumped out to create a vacuum. This is the X-ray tube. A typical X-ray tube consists of a tungsten target called the anode, which is the positive side, so tungsten target, and the filament or the cathode, which is the negative end. There are three conditions that must exist for X-ray production to occur. First, there has to be a source of electrons, which comes from the tungsten filament wire found in the cathode. There has to be a high voltage to accelerate electrons from the tube. And if you remember, we've talked about the high voltage circuit that would accelerate or increase the electric current from between 3 to 5 to 50 to 100. And the third condition is there has to be a target that is capable of stopping them, which is found in the anode. So there are two parts of X-ray tube, the anode, which has the tungsten target and is the positive end, and the cathode with the tungsten filament wire, which is the negative end of the X-ray tube. Let's talk about the cathode. It is negative in nature. Remember, it's the negative end. It consists of a thin coil of tungsten filament similar to that found in an electric light bulb. So this is the X-ray tube. This part right here is the cathode, and in the cathode you will see a filament that is similar to a light bulb. Its purpose is to supply electrons necessary to produce X-rays. It does this when electricity flows through the wire coil and then the wire heats up, it turns incandescent, and the term for that is thermionic emission, and the electrons are produced forming a cloud of free electrons. So electricity is supplied here, and then the electricity heats up the filament wire, and then this filament wire produces an electron cloud. The hotter the filament becomes, the more the electrons are produced at the cathode. So the milliamperage selector or the milliamperage control dictates or determines how much or the amount of electrons that will be produced. The filament, so let me clear this slide. The filament, which is this one right here, is 1/2 inch or less in length, and it is composed of tungsten. You need to know that. Filament, tungsten. So the distance from the cathode or from here to the anode is less than 1 inch. So tungsten, it is used because it is an excellent conductor of heat, so electrons are produced easily. On the cathode, we will also find a focusing cup. This is the focusing cup, and this focusing cup is made up of molybdenum, and you should know that as well. So this focusing cup surrounds the filament wire, and it helps to shape the cloud of electrons so that they will all strike a specific area of the target called as the focal spot. In other words, the focusing cup, so let's look at this illustration here. The focusing cup directs the electrons towards the target. Now let's look at the anode or the positive end of the X-ray tube. The primary purpose of the anode is to provide a target or stop or significantly slow the high velocity electrons, converting their kinetic energy into X-rays. The anode is composed of a copper stem and a tungsten target. The tungsten stem, which is this one right here, is also known as a copper bar, and it has a tungsten plate, and the plate is known as the target that is embedded, and it faces the focusing cup of the cathode. The copper stem or the copper bar is set at a 20-degree angle facing the cathode. So this is angled at 20 degrees. And on the target, which is made up of tungsten, you will find a rectangular shape focal spot. That focal spot plays an important role in determining radiographic image sharpness. The smaller the focal spot, the sharper the image produced. Again, the smaller the focal spot, the sharper the image produced. Before we talk about X-ray projection, let me tell you this. If you have two important things to remember about the focal spot. It is that X-rays originate at the focal spot, and the smaller the focal spot, the better the sharpness of the radiograph. Those two things are very important to remember. Okay, so before we can start, of course, we must turn the machine on and set the control settings. We need to choose the correct patient size, and of course, as we choose the correct patient size, the exposure time will automatically be changed as well. So our machines, as I've said, have preset milliamperage and kilovolt peak setting. So next, we need to press the exposure button and hold it down, and don't let go until you hear the beep and see the indicator light. Remember the deadman switch? Okay, so once you press the exposure button, this causes the electric current to enter the filament circuit of the X-ray machine. Okay, so exposure button is depressed. Now electricity is supplied to the filament circuit. So we're already there. From the outlet, the step-down transformer will reduce the voltage from 110 volts to 3 to 8 volts. And then electricity will enter the filament circuit. Once it enters the filament circuit, the filament will be heated up in the cathode, and then the electron cloud will be produced. So how many electrons formed is dependent on the milliamperage selected. Again, milliamperage, the number. The higher the milliamperage, the more electrons are formed. So once they're formed, these electrons are waiting at the focusing cup to be sent across the anode. So remember, the focusing cup will keep the electron clouds in shape until the high voltage electricity enters the cathode and anode circuit. So low voltage electricity to create the electron clouds, and then high voltage electricity. This is where the step-up transformer will start working and supply high voltage electricity from 60 to 100 kilovolt, and it will give enough force to repel the electrons waiting on the focusing cup towards the anode. And then they will travel from the cathode to the anode, and the electrons will be stopped by the target at the focal spot. The energy on the focal spot is converted into 99% heat and 1% X-ray. Again, 99% heat, 1% X-ray, and then the X-ray will now exit the port. X-rays that exit the port are called the primary beam or the X-ray beam. So the PID, or the position indicating device, sits over the port, and its purpose is to aim the primary beam at the object being X-rayed. Let's look at the X-ray beam and its characteristic at the focal spot. It is said to be polychromatic, meaning having many different wavelengths. There are soft wavelengths, which are longer, low-powered X-rays, and they are removed by placing a filter which is made up of aluminum in the path of the X-ray beam. So it filters. The primary beam and X-ray beam is divergent, meaning it travels in a cone-shaped pattern. When the beam exits the port or the window, a lead collimator is placed on its path to further restrict the size of the X-ray beam. So we've talked about the primary beam or the useful beam. This is what is produced at the focal spot, and it is in a cone-shaped pattern. And the center of the primary beam is called the central ray. A filter is also placed on the path of the beam to remove the soft X-rays and just have the hard X-rays as the primary beam, which is also made up of aluminum. Intensity. When we talk about X-ray beam, we also look at the intensity. When we say intensity, this refers to the quantity and the quality of the X-ray produced. So again, quantity refers to the number of X-rays in the beam, and quality pertains to the penetrating ability of the X-ray beam. So the intensity of the X-ray beam is affected by the milliamperage, by the kilovolt peak, the exposure time, and the distance that the beam has to travel. Intensity refers to quantity, which is the number, so it's something to do with milliamperage. The quality and penetrating ability has something to do with the kilovolt peak and exposure time. That concludes chapter 3. If you have any questions, write them down, and we are going to discuss them when we meet in class.